Okay, let's continue with the actual course content. We have a lot to cover today, so let's try to be efficient. Okay, so last time we have talked about various framing of the question answering task in NLP. And one of those was open-ended question answering, where we have asked the model to produce answers to typically factoid questions and questions posed in natural language. The domain open part refers to the fact that there might be some relevant context for this question, but we as the users do not provide this context to the model. Rather, we expect the model to figure out in whatever way what the relevant context is, and then find the actual answers based on that context. So last time I showed you that little illustration with the question of when are hops added to the brewing process. This is an example of an open-ended question by the fact that it does have an actual answer. So the answer itself is not open or subjective. Rather, we didn't give some relevant pages to our system. The system itself needed to find relevant page, for example, here on Wikipedia, and then extract the answer from that context. We also are not going to give any answer choices to a model that should do open-ended question answering, of course. And the general idea of how to approach open-ended question answering is to automatically find relevant context and then have the model make a prediction of what the answer is based on that context. And you might think, okay, but today we are working with these large language models, and we have learned that they have been pre-trained with this massive amount of data. And we have also kind of learned that some of these relevant information will be in a way encoded in the weights of these models, and then they can use it to retrieve relevant answers, right? Like that's the kind of premise of just prompting LLMs. And so why do we need to retrieve the context? The context still needs to, or it has been shown these days to be still a useful component of these systems, because you might ask about something that the model has heard about for the first time. So information that is actually not being represented in the pre-training data. Or the other issue, more common issue, is that, yes, the models have seen lots of data and they have actually been encoding useful knowledge, but there is so much knowledge to encode, right? So models are not so powerful to just remember everything and be able to retrieve it on fly for every single thing we want to do with them. So retrieving is still useful. And it's actually these systems you're going to learn about today are, I would say, one of the common business models in the large language modeling world. Okay, so this is the overview of 3 different approaches to getting an answer for a given question. The most simplest way, the one which is the most connected with what you know right now, is to take some pre-trained language model, give it a question as a prompt, and get the answer back, right? And as I've just told you, this might be a viable approach and definitely one to try, but still giving relevant context can be useful because models might have either didn't see the relevant knowledge, or they forgot the relevant knowledge, or whatever else. So another approach to answering questions is based on retrieving the relevant knowledge. So basically, you have 2 components of your question answering system. One is the retrieval system that has some external data store, such as a collection of Wikipedia articles. And given your question, it first finds which of these articles are the most related to your question. And then you give those related documents to another component of your system responsible for answering the question. And based on the question, relevant documents obtained through the retriever, this new component is going to answer the question. However, as you can see here, I have 2 different ways of going about this. One is based on basically combining the retriever with what you already know, prompting LLMs, right? So you get the relevant documents and you just put them as a part of your prompt into your model, and then it generates the answer auto-regressively again by doing the next token prediction. Something that was more popular in 2018 when BERT was released is to, given a relevant document, try to find a span in that document that answers the question. So for example, in the same example of when our hops added to the brewing process, the retriever should find the Wikipedia article on brewing, then it should find this chunk about boiling, and then within that chunk, there is this span, the boiling process. So the idea of finding the span in a given piece of text is based on finding where does that span begins and where does it end in a given document. Okay, so we are going to see today how to go about retrieving documents, so how to do this part. Then we are going to go into answer extraction. So how do you extract the span given a document, something that was more popular a few years back? Then we are going to see retrieval augmented generation, which is based on not extracting the span rather than generating by next token prediction. And finally, we will see how do we go about joint training of these retrieval and answer components. Okay? Any questions about this so far? All right, let's go into retrieval then. The first thing I want to mention is this term maximum inner product search, or MIPS. This is the problem of determining a small subset of items in a data store whose representations, so vector representations of that small subset, have the highest dot product with a given query vector. So I'm given some query, I represent that query as a vector, I have a data store, all of my items in a data stores are also represented as a vector, and MIPS is just the argmax equation, finding the document in the data store that maximizes the dot product between the vector representing that document and the query. And although there is obvious linear time implementation, your data stores are typically huge, right? You might have 10 or even 100 million of documents in your data store, so you want to do these dot products efficiently. So there is a whole line of work and tools and software that tries to do this product, dot product between these vectors more efficient. So basically making this search for the vector that maximizes the dot product with another vector as fast as possible. So you will see that term. Okay, so if we have our data store, one data store, and we have our question, one classic way of approaching this problem of finding then the document that has the maximum similarity with our question is to represent each one of the documents in our data store and the query or question document using some vector representation. And way back then, with more classical approaches, people would use our TF-IDF representation. So TF-IDF is something I have mentioned in maybe like a second or third lecture of this course a while back when we were still in summer. So quick reminder that TF-IDF is a measurement of a token and a document. So given some token, we are measuring first the TF value, which is how many times that term, that token appears in a document. And we also have the inverse document frequency, that's n over the number of times that, the number of documents that this term had appeared in. This value here, remember, serves for if this term had appeared only in a single document, the IDF value, the inverse document frequency, will be the highest possible, because if you divide n with anything larger than 1, you will get smaller value. And the idea is that if this term had appeared in one or very small number of documents, it is special in some way, right? It's a really important feature of a document because it's going to make this document appear different than all of these other documents where this term hasn't appeared. So this is how we define TF-IDF. And then we said, okay, TF-IDF is a single number of a term given a document. How do we make a document representation? Well, we just stack TF-IDF values of all the terms in our vocabulary in an order that tokens are indexed in the vocabulary. So if the token with an index 0 in the vocabulary, its TF-IDF value will be first value in the document that we produce in this way. Okay, so this is just a refresher of what TF-IDF is and how do we use it to build a vector representation. Now, some of you might have heard about BM25. I don't need to talk too much about it. What I want you to know, it's basically TF-IDF, but it has two additional hyperparameters. One is that the hyperparameter that adjusts the balance between the term frequency and the inverse document frequency, and another hyperparameter which controls the importance of document length normalization. So it's just a fancier TF-IDF, right? And when we say BM25, you can think TF-IDF with additional hyperparameters. Okay, so we can use TF-IDF to represent our question as a vector of the size of the number of tokens in the vocabulary. And we can represent each one of the documents in the data store as a vector with the size of the number of tokens in the vocabulary. And now that we work in a vector space, we can use our standard vector similarity as a way to measure how related a document is to a given question. Okay, so that's a classic way of approaching retrieval, finding relevant documents. Note here that when we use this similarity, we didn't really do any kind of extra optimization. So going back to the maximum inner product search, here we just try to find the maximum document using the, let's say, dot product between these vectors. We didn't do any extra approximations of this search procedure, so this is still going to be slow. Okay, so that's one component of classic information retrieval. The second thing you will see in this line of work is the inverted index. So for each one of these terms and documents, we need to calculate term frequency. We need to calculate the number of documents where this term appears. And we want to do that way more efficiently. Okay, so to make this calculating these values that we need to actually calculate TF-IDF, people in classical information retrieval have introduced inverted index, which is basically a data structure that enables us to calculate and retrieve these values like term frequency and document frequency more efficiently. So it's nothing fancy, it just enables us to do that. And it contains two parts. One part is this dictionary part, and the other one is so-called postings. Dictionary is something you have seen for yourself many times, something I would refer to as also vocabulary, where you have your tokens, right? So here maybe how is love nor sorry sweet. These are the tokens in the vocabulary. And then each one of them will also have often a value here in these brackets that says in how many documents this term appears, which is useful for calculating inverse document frequency, which is n over, where n is the number of documents in your data store, over document frequency. So this number, document frequency, is what appears here in the red. Okay. And then for each one of your tokens, you are going to record these postings, which is just a list of document IDs. So here, 3, 1, 2, 4. These are documents where each one of these terms appear. So the fact that there is 3 here means that the document with the ID 3 in that document, token how appears. And in the brackets here, 1, you will also record the count of how many times this term here how appears in this specific document. So just to go over it one more time, you have the dictionary of your tokens, something we have called vocabulary many times so far. Each one of the tokens, for each one of them, you are going to record how many times, in how many documents this token had appeared in the data store. And you are also going to record in which documents this token appears. And for each one of those documents, you are going to record the number of times this term appears in that document. Okay, so it's just a data structure which enables us to calculate all the things we need for TF-IDF, which we then consequently use to make vectors. And then we use these vectors to measure similarity between the question or query vector together with each one of the document vectors in our data store. All right, so now question for you. Why could this classic information retrieval approach be limited? What could go wrong? Yes.
It's possible that you could have something in your vocabulary that multiple meanings, and so you retrieve documents that are not associated with the question.
Yeah, that's exactly what could go wrong here. So as we had this issue previously when we started this course, where you have things that either have multiple meanings or things that are synonyms, but not expressed exactly, as TF-IDF didn't capture that all the way back, it will also cause problems here, right? So imagine a situation where you had asked a question, but you have used words that are exactly synonyms of words that appear in a relevant document. So there is no overlap between them, right? So you would get, for example, if we had synonyms, I keep mentioning that basin, right? Sorry, no, that was the word with multiple meanings. Synonyms like, I don't know, why am I always blanking on providing examples of like great and an amazing are to some extent synonyms, right? So when we calculate TF-IDF here, and check how many times great had appeared in some document where amazing had appeared, we will get the 0, right? Whereas there is some connection between this document and that query. So that's not great. As always, we didn't like those approaches where we don't have this flexibility, right? Where everything is too crude, where you have to have exact match between words that are used. Okay, so this is also referred to in the information retrieval space as vocabulary mismatch problem, where the user posing a question or query needs to guess exactly what words the writer of the answer might have used, which is going to be hard. Okay, so I should have not shown you this immediately, but I'd rather ask you what could be a solution here. And given the trajectory that we have taken in this course, I hope in everyone's head immediately you could imagine that instead of working with this TF-IDF representation, we can use more dense and more rich contextualized representation of our documents and our question or query, and then use vector similarity in that space, right? Okay, I will come back, and if I forget, please remind me. Why did I then even mention TF-IDF, right? Like, okay, we have started with TF-IDF in the beginning of this course to ease you into the more complicated representations. But why now when you have learned way more complicated methodologies? So remind me if I forget, why did I still choose to remind you of TF-IDF? All right, so how can we go about retrieval but use fancier vector representations? So one way we can go about this is to use encoder-only transformer that is pre-trained, such as BERT, where we can concatenate in the input our question or a query and our passage or document in our data store, and do that for every single one of the question documents pair independently. So for a single query document pair, we concatenate them together. With these encoder-only models, remember, we always use this special separator token whenever we have two sequences that are different in some way. So here we want to kind of hint to the model, okay, this is one sequence and this is the another sequence, right? So we have that special separator token. So we start with a single string, which is query, separator token, document tokens. Just a single documents tokens, okay? And then we put it into our model, which then we know that each one of these tokens will have its own representations. Then we will mix them together. At the end of all of that, we will have token embedding for every single token in the input again. And remember, with the BERT approaches, we have also in the beginning used that special CLS token. And then I said, well, when we use the encoder-only models, we typically assume that the CLS tokens representation from the final layer represents the entire sequence. And that's what we are using here as well, right? So the token representation of the CLS token is the representation of the entire sequence, which is a joint representation then of query and a single document. Perfect. Now that we have that here, that's called Z, we can just use our output layer, which is, for example, softmax of the logit, which tells us whether these two documents are relevant or they are not relevant, right? So you can think about this as a binary classification. Are these query and document related or are they not? Any questions about that? Yes.
You have to train a BERT model specifically to do this aspect?
Yes, yeah, fine tune it. Yeah, always fine tune it. Yes, you need, because you have this special matrix U here, which are new parameters that you have introduced into your model. Yeah. All right, so can someone tell me what do you hate about this? Is there anything you dislike about this approach? It is, but not really, because here, remember this U here is just a matrix, which will give you two-dimensional vector, right? That you will then normalize. And then you can take value related to related class to be the score of how related they are. So you still have some score you can retrieve for it. But the fact that we'll approach it as a classification will help us later with training, which I'll come to. Yeah. Process. Yeah, right. So here, for every single question document pair, so let's say we have 10,000 questions and we have 100 million documents in a data store, which is completely reasonable. We have, what, 1 billion pairs that we need to encode with BERT. And that's a lot of data to be encoding with BERT. Like BERT by today's standards is not a huge model, okay, right? It's 100 million, or if we use a larger version, it's 300 million. It's not terrible, but it's still substantial, right? So forward pass, it's not so quick, right? So processing all of these question document pairs is gonna take a lot of time to even represent them. But then, as we just said, we want to also additionally fine-tune this model to be specialized retriever for the task. which means that we also need to compute gradients. And then we have learned last time that this is all going to take a lot of memory, right? So it's just a lot going on here. Is there any way you could at least minimize the number of forward passes with BERT? Like, what would you do? It doesn't matter if it's the best approach, but what is the simple modification here with which we don't need to process that many pairs? Okay, I'll give you the answer. So here we are combining each query and document into a single sequence, right? Another trick we can do is instead of producing a joint sequence of a query and document, we process them independently. So each query is going to go through BERT on its own, and each document is going to be passed through the BERT independently as well. So now think about this. When you combine them in a single sequence, if you had 10,000 and 100 million, then you have 1,000 times 100 million combinations. If you do this independently, then you have 100 million plus 1,000 forward passes with BERT, which is 1,000 times less, right? Of course, what are we losing here? Like, why is this nicer than this? This one is nicer because of efficiency, but what is nice about this one? Yep. Exactly, right? Like, so here, at each layer, every single query, every single document token is contextualized with respect to each other. Here, we get a representation of a question that's independent of a document, and also document is independent of the question, and only at the end, in this single final push, we are trying to measure their similarity, right? So what we are losing with this approach by gaining a lot of efficiency is that expressivity of this model is worse, okay? So just to go through this one more time, with this approach, you are encoding query or question independently by passing it through BERT and taking CLS representation at the final layer as a representation of a question. And then independently, you put document through BERT as well. And then you take the CLS representation at the final token to represent the document. And then you take dot product between these two vectors to measure their similarity. Kind of nice here is that in this approach, these also authors, not that only did they separate everything, but they also had kind of remove this additional matrix, right? So it's just a score, immediate score here. So we get the product between these two vectors to be the score of how relevant the document is for the question. This approach is called DPR. It stands for dense passage retrieval, and to this day, it's still very commonly used. All right, now I will give you another way. It's not substantially different than the second way we have seen here, but there will be a little bit more of operation. So basically, we are doing the same thing by putting query and document independently into BERT. However, here, to kind of regain a little bit of that expressivity in modeling, whether like producing expressivity in producing a joint representation, a joint vector of a question and a document, in this approach called Colbert, again, another one very used to this day, is to first normalize each one of the token embeddings coming from BERT. And then for each one of the tokens in your question, so each one of the question's tokens, you take its normalized token embedding, and you are looking for which token in the document embeddings has the maximum similarity with that questions tokens embedding. So for each one of the question tokens, you are checking which token in a document is the most similar. And you, instead of having a single score at the highest level between question and document overall, you are at each token level, you are checking which document is similar, documents token is the most similar, and then summing those similarities. So the score measurement in the end is done by looking at each questions token and not just the overall question similarity with the document. Is this distinction clear? Because this equation looks way more complicated than it is. I'm happy to read it one more time. Yeah. Yeah, so here you have a single question, right? Single vector for a question, and you have here a single vector for a document. And we lost complete interpretability with this, right? We don't know what exactly is encoded in this, right? And then whatever is encoded in this question vector and this document vector, and we are hoping everything important is captured, we are just doing the dot product between these two vectors and say you are this related or not. Here you are giving a little bit more power to your model by going for, across your tokens in your question. So you look at the first token in your question and you check for this token, which token in a document is most related. And you say, okay, there is this similarity, right? And then you move to the next one and you say, okay, for the second token in a question, it seems like fifth token in the document is the most similar and the similarity is this much. So you just have somewhat like a more fine-grained measurement of similarity between these two. Yeah. Okay, so that's Colbert. Any question about Colbert? Yes. For this by second method, you mean this one? And what do you mean? Oh, so okay, is the question, can we first represent our entire data store and then move to our questions, right? Yeah, that's a great question. And actually, let me just go, we'll come back to all of this, but this is also related to the question of what is the index now? Previously, the index was this, the index was a data structure that made the computation of TF-IDF score efficient by reporting the number of times the term appeared in each one of the documents and so on. But this becomes irrelevant for the indexing in the dense retrieval. So index and through saying all of this, I hope I will also answer your question, but let me know if not. So indexing, in this indexing phase of our dense retrieval, we are first gonna cover all of our construct all of the vectors for both the data store documents and for the questions. And you are right, it just makes sense to go first, represent the entirety of the data store, and then look for the questions. And questions will also come right later. Imagine Google search or something like that. Questions are coming all the time. So of course, we are gonna have the vectors of the data store actually stored somewhere, and then we are going to build question vectors as needed. So yeah, going back to what you didn't actually ask about the index, once we have constructed all of these vectors, there are ways to do the search for the vector that's most similar in a slightly more smarter way. And there are a bunch of software for doing exactly this, for doing that MIPS faster. One of them, which is probably the most known or most used, is FICE, which is developed at Facebook AI at the time, FAIR, which is now Meta Research. And the way they go about finding which vectors are the most similar is to first creating the index of all the vectors by clustering them in similar vectors. And then instead of doing the search across all of the vectors, you can be smarter by first looking maybe at which cluster is the most similar, like which centroid of which cluster is the most similar to the query vector, and then go into that cluster instead of the entire data store. So this is what these approximate nearest neighbor search algorithms are going to do. So yeah, what is important to remember here is that the notion of the index has changed from when we use the classical information retrieval approaches. And when we say index today, when we work with dense retrieval, we mean that, okay, we represented the documents in our data store and our question with the vectors, but we are also doing some kind of structuring of that vector space to enable the nearest neighbor search faster. And if that's important for you, for sure, you're going to use this library. It's super well optimized and well written. So it's really good. Okay, did I answer your question? Yeah, okay. All right, so let's go back to this slide. So these are approaches to dense retrieval, but how do we train them? How do these models give you high scores for question and document that are truly related, and low score for query, question, and document pair that are not related? Well, we need to fine-tune this model. And the way to do that is to have both examples that represent query or question document pairs that are truly related and pairs that are not related. And then to maximize the similarity of those that are related in this vector space, and to minimize the similarity or maximize the distance of those that are not related. So let's go over this idea in more detail. So our objective is to train a model to predict the relevance of a document to a given query by optimizing a similarity score in a vector space. For example, similarity can be dot product between vectors. To do this, we need training data, and our data will need to have positive pairs of question and documents and negative pairs of questions and documents. Your positive examples, pairs that are truly relevant, usually comes from data where this relevance is manually labeled by some human annotators, and that presents your gold standard. So some people have said, for this question, you need this document. So this Wikipedia article, for example. So you're sorted out with positive examples, you just need to find an appropriate data set. Okay, go to Hugging Face datasets and find a data set that works for you. Negative examples are trickier. Remember, we already had this training with positive and negative examples, where negative examples have to be constructed when we were talking about how to train word2vec. So this is not first time you're seeing this kind of training. Just a reminder. But yeah, the question is how do we find documents that are not related for a given query? And that seems to be easier problem to some extent, because you can just use some random documents and say, well, most likely they are not going to be related, right? However, in this community, people have found something even better, and that's to use whatever is an existing retrieval system that you want to improve, and get top K relevant document, let's say top 1,000 relevant documents from this imperfect retrieval system. And then you are using those as your negative pairs. Why would we do this? Well, we want to make things challenging for our models. We want the model to learn deep connections between what distinguishes a document that's relevant to a given query from a document that's not relevant to a given query. We want to go beyond some very shallow surface level cues. So to make the model smarter, you want to challenge it more, right? Like as we give you challenging exams, that's similar notion here. You give some pairs that are not so trivial to distinguish from positive, truly relevant pairs. Okay, so this is why we actually use the top 1,000 ones that are coming from imperfect retrieval system and use those as negative examples. Okay, I will make things slightly more complicated before I tell you how we use these positive and negative examples. But in Colbert, besides, just a moment, if you can. Besides doing that more fine-grained similarity measurement, in Colbert, they have also proposed what to do if you do not have positive examples labeled by human annotators. And they said, well, again, use your imperfect information retrieval system and get top K ranked documents. And then in your data, label data, you have to have the answer. That's requirement for either of the approaches. Then use those documents retrieved from an imperfect existing retrieval system that contain the actual answer as a string in their text as positive examples. And use others that do not have this string contained in their text as negative examples. And then train your new retriever for some times. And then at some point, repeat the construction of positive and negative pair with your intermediate retrieval system you have trained and continue. Okay, so you are refining your system, and as you are refining it, you are also using it to construct even better positive negative pairs. Okay, I will come back to how we actually use this data, but I want to take your question first. Mm-hmm. Yeah, so usually how these data sets are constructed are, you tell your annotators, all right, so here is some question or here is some fact, and to answer this question or to verify that this fact is true, can you identify on Wikipedia which article is relevant and can help you come to the answer? So instead of looking at all of the positive or negative examples, they're actually just telling you, well, you should be using this one, right? And this is based on some knowledge that these annotators are having. So for example, if the task is question answering in machine learning literature, you would hire a machine learning researcher who would tell you, well, to answer this question, you need this paper. So this paper now becomes your relevant document for the retrieval among, let's say, all of the archive publications.
We consider them as negative samples since they're in the 1,000.
So let me think about this. Just trying to figure out what do you mean exactly. So when we label one document as relevant for one question, you are concerned with this example being negative example for some other question or for that same question? Mm-hmm.
And one of them is chosen as positive. There is a chance you consider it as negative because they're in 1,000
Uh-huh.
Yeah, then but they're not negative actually.
Okay, I am sorry. I just have a hard time. I'm not saying you're wrong or correct. I just can't follow exactly what do you mean. So maybe after the lecture we can talk about that. Thanks. All right. I didn't bring my water bottle. If I crash here, you know what's up. Okay, so training. We have now these positive and negative examples. And what do we do? So this is just another way of representing the dense retrieval that we have seen over here. So this visualization over here is just another visualization is shown on that other slide over here. All right, so this is the equation we are going to use. We again have that negative log of something, negative log always there for negative log likelihood training, but negative log of what exactly? So here at above the fraction line, you have the exponent of the similarity between your question and the positive pair. And here you have just a normalized the similarity of your positive pair together with all of the other similarities coming between the question and your negative passages or negative documents that are not relevant. And this is an instance of contrastive learning. So here, basically what you are doing is with every iteration, you are making you are changing Bert's weights, which will consequently change the representation of your question and your document that's actually relevant for that question in a way that when we make their dot products, those dot products will become higher. Whereas the representation of documents that are not relevant will now in the next iteration of the gradient descent become such that the dot product between them and your query vectors are gonna become lower. So this is what is happening over here, kind of visualization, which is provided here might help you visualize that. If you start here, then after doing one gradient descent with this loss function, your positive example will come closer to your query vector, where your representation of a document that's not relevant will be pushed farther. So that's what's happening with this training. Okay, so that's as much as I have to say about training. Are there any questions about this? All right, so I told you about the index. Don't forget, the notion of the index has changed with the dense retrieval relevant to the standard, more classical approach. Okay, so final thing, I think that's final thing I want to say about retrieval, or maybe second to final, is how we go about evaluating them. So we have a data store, we have a question, and then for each one of them, we can decide either we get a score of whether they are related or not, and we can threshold that score to say, well, all of the ones above the line, about the threshold line are relevant, or you can rank them by the score and then say we are going to pick top 5 to be relevant and everything else to be irrelevant. If you have that softmax, which behaves as basically relevant or not relevant predictor, then you would just get those that are predicted to be relevant. In any of these approaches to deciding what's relevant, how do you then decide whether that's good or bad? Well, you are going to again use precision recall FF1, which here will have particular notion specialized for retrieval. So precision will be the number of relevant documents among all of those documents that are retrieved to be relevant. So if you score all the documents and you say top 3 are relevant, then amongst those top 3, you can check in your data set, in the test set of your data set, what did your human annotators of that data set say about whether these documents are truly relevant or not for that query. That's how you measure precision. Then for recall, your human annotators in the data set have said, well, these documents are relevant for this query. And then you check how many you have actually retrieved. And then as always, F1 will be the harmonic mean between the precision and recall. The issue here, and I'm not going to go into that, and you can check Juravsky and Martin if you're interested, is that this measurement does not tell anything about how good your ranking is. So even if you had retrieved, let's say there are 3 documents that are relevant for a given query, and you have indeed retrieved all 3 of them, but let's say that the ranking is 1, 2, 3 by human annotators, and yours is 3, 2, 1. So you did retrieve them, but the importance is exactly opposite from what your humans have said. you wouldn't penalize your retrieval system at all, right? So this measurement useful. You can use it, of course, you should use it, but it doesn't tell you whether your ranking is good. It's just telling you whether you retrieved well or not. Okay, the last thing I want to finish on on the topic of retrieval is that retrieval today had way more advances because it's becoming this super relevant thing for generating text that's factual and so on. So we don't have time to cover all of these things, but I do point you to this amazing tutorial on the retrieval-based language models from ACL last year. ACL is our top conference in NLP. And the organizers of this tutorial have divided or categorized these new approaches to retrieval in 3 categories, which is relevant and is going to become more relevant when I tell you about generation of answers based on these retrieved documents, right? But for now, since you know what large language models are, you can imagine we have taken relevant documents, we've concatenated them together into a string, we put question at the end, and that's our prompt. And we gave this prompt to an LLM like Llama or Qwen or ChatGPT or whatnot, and it generates the answers for us. So in this approach, retrieval has other considerations, such as if you are generating 10 tokens, maybe what you need to generate first token is not the same document you need when you are generating 6 tokens, right? So the notion of what's relevant might be changing as you are decoding the text. So when to retrieve is a question we will have when we move more into this retrieval augmented generation. There is also, we can do retrieval at different layers, not just at the output layer as we have seen with DPR and Colberts and so on. And some models of retrieval do not retrieve just text chunks, rather they might retrieve tokens or entities or something else. Okay, so I'm not going into details of any of this. I just want to tell you, I gave you the basics of retrieval, and they're not useless basics. This is still something you would use, DPR, Colberts, that's something we are using to this date. But this landscape is quickly changing, you know, as you have seen. Every time I showed you, okay, this is new line of work, there is a huge taxonomy of new things that have happened. Retrieval is not, you know, excused from that trend. So just know that there is a lot of happening in this space. And if you are interested, I recommend you go and check the tutorial. There is also recording and slides there where you can learn way more. However, we have lots else to talk about. So far, we have just retrieved the documents, right? But our goal is to actually answer questions. So we need to talk about, what do we do now? Now that we have a relevant document, how do we display an answer to the user? And here we are going to talk about 2 approaches. One is approach where we extract the answer from a given document. And the other approach is where we generate the answer using next token prediction. Okay, so let's start with the answer span extraction. So imagine we have retrieved a relevant document. And for the simplicity, imagine you have just one document that you have retrieved as a relevant document. What you're going to do with this approach is, again, make a joint sequence of your question and that relevant document, or reuse one if you already have that representation. So with BERT approaches, again, we have that separator that kind of separates the questions from the document tokens. With LLMs of today, which are more decoder-only transformers, you would use something like passage column, right? Whatever you choose, you need to kind of signal to the model, this is a question, this is a passage, if you don't want it to work too hard. Given context, this new related document and the question, our goal is to predict which token in that relevant document is the beginning of the answer span and which one is the end of this answer span. Once you have predicted that, you can just extract that answer to be the predicted answer, okay? So is that clear? I don't have the visualization of that, but if I'm giving to the model here as a passage some tokens, let's say I will call them just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say that the answer span is spanned through the tokens 2, 3, 4. Then the model should predict that the second token, you are the start. At the fourth token, it should predict you are the end. And once we have that information, well, then we just use the, if we have a tokenized text, we just use, okay, from this list, which is a tokenized text, we use index 2 to 4, and then we merge it together with white space or whatever else we need. Okay, so how do we predict for the tokens, whether they are start or the end? Oh, sorry. This is a little bit wonky. Sorry, I was tweaking this before the lecture, and then I missed to add something. So in the original BERT paper, if you read how they approached this problem, they introduced two special vectors called start vector and end vector. These vectors will be of the size of your embeddings that come from the final layer of BERT. So at each one of these tokens, you have as the final representation from BERT, final representation of that token. So here, for example, for P1, which is the first token in the relevant document, you have as the output of a BERT token, new token representation of that same token. And then you use this specialized start token, start vector, and you make a dot product between the token embedding for, let's say, first token of your passage with that start token, and that's a dot product. And you can use that product to say something about likelihood of that token, the first token being the likely token to begin the answer sequence. So as always, we have that notion of similarity related to the likelihood of something being the case. And here we just at each token are checking, are you the start or are you the end, right? So the final probability of whether the token I in our related passage, the one that we have retrieved, is the start of the answer sequence, is given by the dot product of that special start embedding with the token embedding of that token and normalize over all of the similarities, right? And similarly for the end. Okay, so is there a question about this one? So we are just going over the final token representations of tokens in our relevant document or passage, and we are checking, is that the one that's the start or the end of the answer sequence? One thing you might ask me, why do we need this start and end vectors? And honestly, I don't know whether they are crucial. So for example, you could have two weight matrices for your output, one associated with start and one associated with the end of answer sequence. And for each token embedding, you could be multiplying those weight matrices to get the probability that this one is the start. I guess here we can easily normalize over all of them. Yeah.
Where do we get this started?
You introduce them to the model and you initially randomly initialize them. They're learnable parameters. Yeah. Yeah, sorry about that. Should have emphasized that. I had like definitions of S and E, but I don't know where they disappeared.
So would it be kind of similar and same thing if we imagine the S and E as different affine layers at the end of our output from BERT, so it kind of like splits into two different passing, it goes through two different assigned layers. Would that be the same kind of idea?
Yeah, if you define the layer to be the dot product between let's say start vector and the final token embedding, yeah, then yeah, I mean we can call these layers. Why not? They're just done, yeah. Like the dot product between these doesn't go into this one, so they're kind of like parallel layers. Yeah. Okay, so I will repeat it just one more time. So I here denotes the final token embedding for the ith token in your passage, which is retrieved by a retrieval system to be the relevant context for this question. Given that token embedding and given some start vector, which is initially a random vector that you are going to learn the parameters of, then you are making dot product of these two values to predict whether this vector, this token, ith token in the passage is the start of the answer. And here you are gonna make the dot product with the end vector to predict whether it's the end of the answer span. And finally, how do we go about training? I don't know what's happening here. I need to fix this. So the final thing we are going to do is the basically for each possible subspan of your retrieved document, you are going to measure the likelihood of that being the answer, right? By combining the score, the scores of basically these dot products, but then here you're just using different I and J, right, to construct different subspans of your passage. Okay, and then whatever you have decided is the probability for being start and end. You're going to combine that in the final loss for training. All of this is implemented in auto model for question answering in Hugging Face. So if you use auto model for question answering and you use, let's say, a name Bert, I mean, you need to use the actual name in Hugging Face. You do not need to implement these output layers. This is going to be created for you. Okay, so this is again nice thing about auto classes. If you use the right auto class, these new classification heads will be produced for you. Okay, few more details and evaluation of this answer extractor is first question you might have is what do we do when we do not have the answer? Like sometimes questions do not have the answer in a given span. And this happened, for example, squad dataset was the one of the very important dataset that were introduced to do this answer span extraction. And then the second version of Squad, which is also very important data set, introduced questions for which models should not answer anything as the answer because there isn't an answer in the given document. And in this case, the people are training CLS token to be the answer, to signal there is no answer. So this is something you will see. You might also ask me, well, we talked about the maximum input sequence length, right? So with encoder models, there is as much as we can fit to get the good performance. And what happens if our relevant document is longer than the input sequence? Well, what do you see with this encoder-only transformer models is this idea of a sliding window, where if the maximum sequence length is 512, you will kind of shift that over your document. So as many windows of 512 tokens you have in your article you are going to consider. And for each one of them, you are going to do this answer extraction part. And this is where this no answer thing becomes very relevant because for most of those, except one, you will have no answer, right? So for most of these windows, you will predict no answer. And then for one of them, you will actually extract the span. Okay, so finally, how do we evaluate answer span extraction. One measurement, which is really easy and intuitive, is to just do the exact match, whether we have predicted this answer sequence which matches exactly the answers that some person in some data set have said that, this is the answer for this question. And the issue with exact match is that it's really strict, right? So you miss an article before your noun phrase, and now you get 0 when the actual content is right. So let's say the answer is the 3 dogs or something like that, and you predict 3 dogs. Now, no exact match, you just missed the, and suddenly you get 0. That's really strict, right? Like, we don't really want that. So what people are using is token F1 score. So you can consider your answer string as list of tokens in that answer string, and then you can check for tokens that your model had predicted, how many of them have actually appeared in the string, in the list of answer tokens, and from those that you should have predicted, how many of them you actually did, and you use the harmonic mean. So you get token F1, which is close to exact match in spirit, but it's a little bit more flexible, and it's in that sense more useful measurement because it doesn't penalize models that are really good but not perfect. Okay, so since this brings me to a retrieval augmented generation, I say let's stop here. We do have a few minutes, so I just want to check, are there any questions about anything we talked about today? Yes.
Like once we have a retrieval system and we pass the concatenated, or it'd be like passages, filter passages, and then question after that. When we pass that to like llama, for example, would that be kind of tested as like a reading comprehension task? Like when it gets to that point, once we've already retrieved the passages?
Yeah, you're completely right. So let me go back here. Oh no, I don't have it. Oh yeah, I do have it. So here, in this visualization, you can see you have that information retrieval component, and then it gives the retrieved documents and does this answer extraction. It's actually called reading comprehension, this box. So once you provide the context and question to a model, that becomes a reading comprehension task. So yes, you are completely right. With these two approaches, with the one I have just explained, answer extraction, we are extracting the answer. And with Llama that you mentioned, we are actually going to do something that comes next, which is generation of the question. So using most recent models that are decoder-only transformers like Llama, ChatGPT, Qwen, Mistral, and so on, you will typically cause problems as that sequence-to-sequence problem, where you are generating the answer rather than predicting at each token in your retrieved passage whether it's start or the end of the answer. So now with Llama, we are entering just a slightly different way of doing reading comprehension, but that's gonna come next time. Yes?
We mentioned bird loss during the lecture. In theory, it could be done with other models, so it doesn't have to be bird, right?
So depends what we are talking about. So what comes next is answer generation. You will use models that are good text generation models. And we have learned that those are decoder-only transformer models, which are pre-trained with next token prediction. So for what comes in the next lecture on Monday, you actually wouldn't use BERT. Here you are right. Yes, there is actually no reason not to use another model. The reason I mentioned BERT is because this approach here has been popular when BERT was popular. And now that BERT is no longer popular and we have models that are text generation models, we are entering this new approach over here. So if you choose to use, let's say, Llama, most likely you will take this approach that comes next rather than this approach over here. But you're right, like you could use other models. as well. Okay, so let's stop now, and then next time we're going to talk about RAG.